All right, let's go ahead and get into section 12.3 here, the dot product. So this is one of these things where you're going to really want to start understanding what this is and not just memorize a bunch of equations for how to use it. If you understand what a dot product really is, then the equations that we'll encounter here become things that you can basically understand and figure out, just as you're doing it. And, understanding, of course, in my opinion, is always more important than memorization. So let's take a look here. So basically, the idea here is in this picture, we're looking at a projection. I told you we'd talk more about projections as we moved along. But the idea here is, again, it's kind of like before. If I shine some light straight down on this, right? Maybe I should do the light arrows in yellow, but I didn't. We would get a shadow. And if that shadow included the arrowhead on it, then it would be a vector because it would have a direction, and it would be the projection of our vector onto some surface. In this case, the surface is represented by the vector v. And so what we have is a vector f being projected onto vector v, and that's what we've got there. Here, we can start to look at what the angle would be between two of these vectors and relate it to this dot product. So what we can do is look right here, and this looks a little complicated, but this is gonna be a lot simpler when we actually look at what a dot product actually is. And so we can do this pretty simply. We can actually replace that whole equation with something like this. Vector u dotted, we put a dot, v equals u, the magnitude of u, times the magnitude of v, right? These were the magnitude of the vectors, so the lengths of them, times the cosine of the angle between them. That's a very important one that you're going to want to remember. And that's essentially what this big thing is right here, all right? It's just written out. It's solved for theta, and it's written out in long form, assuming you didn't know how to actually calculate that dot product. Okay? So if we look here, we actually get how we calculate the dot product. And you'll notice that we say u dot v. That's what this would be, u dot v. And the way to do it is to simply multiply the like components. So the I components or the x components multiplied together plus the x components or the j components multiplied together plus the k components or the z components, whichever you want to call them, multiplied together. And then you add them up and you end up with a scalar. All right, so this is the dot product. Sometimes people call it the scalar product because you're taking two vectors, you're multiplying them together, and you're getting a scalar that represents then the multiplication of those together. Now I want you to notice what we're doing here is multiplying parts. I'm not sure why that happened again. Sorry about that. But what we're doing here is multiplying parts together that have that are parallel to each other. Okay? And so that's what we're doing here. We're multiplying all the parallel parts together, and we're getting a result. And so that's the idea of a dot product. You multiply all of the parallel parts together. Okay? And so, of course, that would mean if you had two vectors that were perpendicular, where is that? That's skipping ahead. I thought it was right there. Yep. If you have two vectors that are perpendicular to each other, then they have no parallel components, and your dot product will be 0. So if two vectors are orthogonal, which, orthogonal is one of those words you're going to kind of want to get used to. Anything that is orthogonal or anything that is perpendicular is orthogonal, but not everything that's orthogonal is necessarily perpendicular. So it's kind of like all squares are rectangles, but not all rectangles are squares. So for the most part at this level, we can use them interchangeably, but if you go further into the future, you may come across situations where they are not necessarily interchangeable. But the idea here is you multiply, you do the dot product of two vectors together, and you multiply all of their parallel parts together. If they have no parallel parts, That means they are perpendicular, and therefore the dot product will be 0. All right, and we'll come back to that in a minute. So this is where we were. So this is our dot product right here, the components together. So if we go back to this page, you can see I can take this one right here. I'm going to move it up a little bit here. All right, this one you need to know, or I'm going to move it over to the side actually. Make sure you know this one. But we can do a step here where we can do cosine of theta equals u dot v over the magnitude of u times the magnitude of v, u dot v. So again, notice this dot product is not the way you multiply scalars together. It's just one of the ways we multiply vectors together. And then that can give us basically that cosine theta equals, and then we do this dot product. Well, that's the dot product right there, right? So actually, let me write this way, so maybe it'll be a little more clear. Theta equals the arc cosine of u dot v over the magnitude of u times the magnitude of v, like that. So you see, the next step would be that step right there where we took this u dot v right here and we expanded it out as the actual dot product by multiplying all the perpendicular parts together, or all of the like components together. All right, so for me, myself, I find this a much simpler thing to remember, and so I memorize that one, and then I can always just do a couple steps to get to whatever form I need, because you're not always necessarily going to need this form down here, because you might already have the angle and you might be solving for one of the magnitudes or something like that. So I personally am a big fan of u dot v equals uv cosine theta. All right, and it's, I think I've encountered it more often in that form. So that's what I would go with. So here was our dot products. Let's try doing some dot products here, you see. And so we have two vectors written in component form. And you'll notice what we're doing is linking up the x components. Excuse me, that's right there. Linking up the y components, that's right there. And then linking up the z components right there. You multiply your pairs together. 1 times negative 6 is negative 6. Negative 2 times 2 is negative 4. And negative 1 times negative 3 is positive 3. Add them all up, and there's your single scalar that represents the dot product between these two. The larger these two vectors are, the larger this dot product will be. The more parallel these vectors are, the larger this dot product will be. And as we continue on with some examples and show you some uses of this, hopefully you'll start to develop an intuition about what this dot product really means. And then of course there's B. You can read through that one. You're doing the same thing. I times I, j times j, plus k times k, like that. And it's easy, you're done. All right, so take a look at this one. This is the parallelogram law of addition of vectors. As I said in a previous video, I prefer something more like w equals u plus negative v, and I really haven't encountered a situation where this doesn't work. I mean, you can always redo it just like this. Here's u, here, let me draw it on here. We already have u. If I draw in negative v like this, if I can get it about the same length, right? Negative v. Again, I'm going to get that same vector w right there going in the same direction. So I prefer that, but if you like this parallelogram law, you're welcome to use it, although I didn't draw my v vector quite parallel or quite the right length there, but it's good enough to see the idea. All right, so let's take a look at this example. Find the angle between these two. Now in this one, they're going back and using that equation that we saw a few pages ago, but they don't have u dot v written out as all the components multiplied together. And so the first thing they do, I prefer to start, I guess, with u dot v equals the u v cosine theta. That's the one I remember, but again, just a couple steps and you get right to that version. And no matter what, if we're trying to solve for theta, we're going to need u dot v. So we're going to need u dot v here. That's being solved right here, doing the dot product of it. And we're going to need the magnitude of u. That's right there. Let me highlight that a little better. And then we're going to need the magnitude of v, which is that being found right there, which u dot v we just learned how to do. You multiply the i's together, the j's together, and the k's together and add up the result. For finding the magnitude of vectors, you should remember from the previous video, we're just using the Pythagorean theorem, right? We're going through and just solving that out. And so we're just finding the length of it by turning it into a triangle or multiple triangles in the case of the 3 dimensions. And then once we get that, we just go through, put it all together, and then find our final answer. Okay? Find our final answer here. Okay? And this works for 2-dimensional vectors as well. It doesn't have to be a 3-dimensional vector. I underlined that poorly. It works for a 2-dimensional vector as well. And so it's easy to use. You just won't have a k component. And you just go through and do the same sort of thing. Okay? Just a little simplified. All right, let's look here. We've got another example. Find the angle. Now, this one I'm going to start for you, but I want you to finish it. Now, remember, when we're doing dot product, it's the angle between the 2 vectors. If you look back here, it's the angle between the 2 vectors. Where was this? Anyway, we can see it in this picture. It's the angle between 2 vectors when you put their initial points together like that. So when we come back over here, what we can essentially do is you have to be careful. We want our vectors to be on either side. So we want this line here and we want this line here. But what we need is we need the vectors to point this way. All right? Be very careful. If you had done like this vector dotted with this vector, right? Assuming, let's go with blue here, or blue. Assuming, this was our picture we had just a second ago, had you done this vector pointed out from the origin and this vector like this, then what you would essentially be doing is getting this angle out here, which, looking at this picture, would be an angle greater than 90. And we need an angle less than 90, just assuming this picture is to scale. So we need this angle in here, which means you have to flip this vector and make sure it's pointed in that direction. And so if we call this vector here u and this vector here v, then vector u is simply going to be, if we look at this, we have components for it. What are my presets? We have components for it. We have a vector component going down this way, or a projection this way, and a projection this way, which we can just turn into components by finding the lengths of them. And so the length of this x component here is simply going to be 0 minus 5, right? It's in the -5 direction. And this one right here is going to be 0 minus 2, right? We're starting at 0, or we're starting at 2 and going to 0, so it's final minus initial, 0 minus 2. So this one's a -2 length, this one's a -5 length, which means that for vector u, we have, in component form, -5 in the x direction, -2 in the y direction, just like that. And then vector v, here, when we look at it, it's going to have components, do them in purple, I guess. It's going to have a component coming over this way in the x direction, so it's in the negative x direction, and then in the positive y direction. So this one is going to be what? It's going to be final minus initial. So in the x direction, it's going to be 3 minus 5. So right there is 3 minus 5, which is a -2. So in component form, we have a -2 there. And then for the vertical part here, we've got final minus initial. So that's 5 minus 2. Right? That's this 5 minus this 2 here. And that's going to give us equals a 3. So that's a 3 right there. And so this is a 3. And so those should be your 2 vectors. Double check me on it. Make sure you understand and can come up with that however it makes sense to you. And then go through and try this one. Use our equation that we just used back here. This relationship, either one, this one or this one, whichever one you find easier to remember. And then go through and solve the rest of this one. But make sure you use those 2 vectors so that you get them in the right direction. All right, here, I talked about this page already. Again, vectors u and v are orthogonal if their dot product is 0. And so let's try one right here. Let's try example A, and I'll leave example B for you to try. So example A is u dot v, and that's going to equal 3 times 4 plus -2 times 6. There's our dot product. So this is going to be 12 minus 12, and that's going to be a 0. So therefore, they are orthogonal. They are linearly independent is a good way to think about that. Try linearly independent. Okay? In other words, what we're saying is if two vectors are orthogonal, there's no way that I can take u, no amount of u's at all, and move in the direction of v at all. So, for example, if this is the direction of u, and this is the direction of v, and they are perpendicular like this, they are orthogonal, then think of it this way. No matter how much I try to move in the positive or negative v direction, in the positive v or negative v direction, I'm never going to move even a single, centimeter or millimeter or atom in the direction of u. They are totally independent of each other. They are linearly independent. The only way I can use v to get u is to do some sort of rotation to it. I can't just scale it linearly and get any amount of any motion in u. However, if they were not, if we had two vectors, say u, let's say that's the vector u again, and I had some other vector w, right? These two are not orthogonal. They are not linearly independent. And if I move along w in the plus w or negative w direction, no matter what amount I do, it's some scaled amount, a tiny bit or a lot, I am also having a bit of my component be parallel to that u vector, right? Where this is going to be parallel to that. So moving in w also moves me in either in the plus or minus u direction. They are not orthogonal. They are not linearly independent. Okay? So, not ortho. Okay? Ortho. Okay? So, kind of keep that in mind. Here are some properties of dot products. If u, v, and w are any vectors and c is a scalar, then u dot v equals v dot u. That one should make sense just by thinking about the definition, how you calculate it. C times u dot v is equal to u times u dot cv, or c times u dot v. So we can do that in whatever order you want. U dot v plus w is, you can just distribute it there, u dot v plus u dot w. And then u dot u is the magnitude of u squared. This is a good one. That's an important one to remember. These are all pretty important. And then if we have our last one here is the 0 vector. Don't forget that's the 0 vector dotted against u gives us the 0 scalar, because again, dot products result in a scalar. All right, here, this one we're going to kind of come back to this picture here, but the magnitude of the force in the direction of vector v is the length f cosine theta. So this comes just straight from triangles, right? Where this is length L, and we can say cosine of theta is equal to L, the length of that, the adjacent side over the hypotenuse, which means that F, right, the magnitude of these, the lengths of these, that means that F cosine theta equals that length, and that's what we have right there. So that's just from back in a little bit of a, our old trig definitions of sines and cosines. And that's what we have right there. And the length of that F is the length of the projection of F onto V, okay? And we're going to take advantage of that in a problem here coming up. Here, you have to be careful. These are vectors projected onto these, so not just, we can use the dot product to kind of find these projections where we actually have the arrow of the projection and not just the length of the projection, but an actual new vector that's in that. So if we project u, the vector u, onto the vector v, we should get a new vector that is like the shadow of u onto v. Even if v is actually shorter than u, we can still come up with a way to do this. All right, and then the same thing over here, it's just projected, the shadow is down, so even though this is v, it's more like the line that v runs on is what we're projecting it onto. Okay, and so you can see we have those shadows there, those projections. The length of the shadow is the component, the actual shadow with the arrow and direction is the projection. And so here we've got another picture here showing this again. This time v is shorter, that's the direction of motion in this case, and the projection of our force down onto v is that shadow in that length there, right? Is this whole big arrow, this big one right here, that's our projection. And again, the length of that projection is the component, and then the projection just, we're using that word like a projector. You project it up onto a screen, and you can see that if we had a projector running on a screen and I held a stick up and changed the angle in front of the screen, I'd get different lengths of shadow on that screen, right? So if we had a projector projecting up onto a screen like this, right, and I held a stick up here, like say a meter stick, if I held the meter stick parallel to the screen, right there like that, then the shadow that would be projected on would be the same length, right? It would just be blocking out the same length. But if I rotated that, if I rotated this so that my stick was more sticking, I guess, out away, I know that's not a very good picture of it. Let me try that again, put a little depth to it, like we had this rotated so it was pointing out away from the screen, then my shadow on the screen would shorten like that, and that would be my new projection onto there. And of course, if we added an arrowhead onto the end of these things, then our shadow would also show an arrowhead, and that would be then the projection, right? So if we had an arrowhead on the end of each of these, something like that, a direction to them, okay? But as we'd rotate, the shadow length would get shorter as we rotated this out away from the screen. I don't know if that picture is good enough to see that or not, but hopefully it is. All right, here we go. Here is the actual projections. And so you can see the links here, and you can see that if our angle, if we're using this projection length here, if our angle theta is greater than 0, in other words, we're on the unit circle with an angle that is over here on this side, so less than 90, then we get a positive projection. If our angle is greater than 90, such that the cosine of that angle is now negative, because we're on the negative x side of our unit circle, then we end up with a negative length that's pointed in the negative direction, just like that. And you can see that in these two pictures. And so here is the projection of u onto v. Now, the way I think about this one is I think I want to project u onto v, and we know that u dot v, if we dot two vectors together, we're multiplying the perpendicular parts together. And so I want to multiply perpendicular parts together, but I don't want the length of this vector v, right? So we have u here, here's u, here's some vector v. I don't want the length of vector v interfering with the length of the resultant vector that I get. So what I can do is actually take the unit vector v, a vector that points in the same direction as v, right? And is that unit vector, I'll put that little hat on it. The unit vector v, oops, I put the unit vector u, sorry. The unit vector v, and have that unit vector multiply, because what happens when you multiply something by 1? You get back the same number you had before, except this time we're getting back just the parallel parts, because then if I look at u, right, u is going to have this component in the same direction as v and this component perpendicular to v. So like this is the component of u in the direction of v. This is the maybe I shouldn't have put a v there. I should put u parallel, and this is u perpendicular. to v like that. Well, when we multiply, when we do u vector dotted with unit vector v, well, what's going to happen is this part right here has nothing that's parallel to it to multiply by. Okay, there's nothing parallel to it. So it's going to get canceled out. And all we're going to end up with is this u parallel times this v, and this v has a length of 1. So the only thing that I'm getting is I'm getting u parallel times 1, which is just u parallel. So evidently, if I dot u with the vector v, I will get a scalar that has the length of the part of u that is parallel to the vector v, just by doing u dotted with the unit vector v. Now, that gives me, again, it gives me just a component. So this is just a component right here, right? This part right here is just a component because it's a scalar when you do a dot product. So what I need to do is add on to that another direction. I need to give it a direction, right? So this is a component, it's a scalar, and then I'm going to take that scalar and I'm going to multiply it by another unit vector v to give me the direction of v. So I have a length here in the direction of v, and then I'm going to multiply it by that unit vector v again to give me a direction in the direction of v. And that should pretty much do it for me. U dotted with the unit vector v times the unit vector v again. If we take a couple steps with this, the unit vector v I get from doing the vector v divided by its own magnitude, its own length, right there. And so I have that. And then again, that's that unit vector v here again. So v over magnitude of v, like that. Okay, magnitude of v. And I can combine these two together, right? I can combine it, and you see over here in this picture, this is a scalar, right? The magnitudes are just scalars. So I can do u dot v divided by, and I can combine those two scalars together into a magnitude of v squared, because they're scalars, I can do that. And then this whole thing just times the regular vector v, and that is this version we have right here. So I'm going to leave it up to you. I personally much prefer this. This makes sense to me. I like this. If I go 5 years without doing one of these problems, I can sit down and figure that out myself by just thinking about how to multiply by 1 and what an actual dot product is doing. I like that one. However, you are welcome to memorize that one, okay? And go for it and use it. Here, this next part is essentially just this part that I did in blue, right? That was what I said was that scalar version, and that's this right here. That's the first little part where you're not actually doing that. So this is the component, all right? That's the component part. That's that first part in blue. And then the projection part is where you do the whole thing and add on that extra v direction onto it. So again, it's up to you, whichever one you want to memorize. This one right here, go for it. If you can follow my thought process on this or come up with your own thought process that gives you that, then go for that one. But dot products are multiplying parallel parts together, and so you can take advantage of that, plus the idea of unit vectors. They aren't going to change the overall magnitude of something. They're just going to give you a part that is, it's going to just basically pick out the part that is parallel to it. And if you want another example of this, think of our coordinate systems here. And let's say we have the unit vector x in this direction, or actually we want the unit vector I, that's what we're using. So the unit vector I in this direction and the unit vector j in that direction. And we have some other vector pointed like this, right? Some vector v. Well, if I wanted to find the component of v, right? If I want... All right, sorry about that. Had a little bit of an interruption there. My dog started barking. So let's see where I was. So but basically, if I want to find the length of v along the I direction, the x direction, then I'm going to do vector v dotted with unit vector I. And that'll give me that length there, okay? And that's going to give me v in the x or in the I direction, okay? If I want to get the component of v in the j direction, I'm going to do vector v dotted with unit vector j. And that's going to give me v in the y direction or the j direction, whichever way you want to put it. All right, that's the components. If I then take those and multiply them times, right, if I come back here, if I multiply this by the j vector, in other words, I'm adding back on a direction, I get the projection of v on in the j direction. And same thing with the one above it. If I, oh, that's not the same color. If I multiply this by the I direction, I end up with the projection then instead. So just taking that extra step takes you from component to projection by adding back on a direction in, well, the direction that you're looking for. All right, so here is an example 5. Find the vector projection of u onto v. And so for this one, this video is getting a little long, so I'm going to leave you to look through this, but think your way through this. All right, try thinking of it with this version that they gave you on the previous one, right? And then try thinking through it also with the way I was trying to tell you to think about it, by thinking of, getting unit vectors and picking out, essentially by using the dot product to pick out parts that are parallel to the direction you're looking for. So see if you can follow through this one and figure this one out, and it should make some good sense for you, okay? But ultimately, it's always the same thing, whichever way you're more comfortable with. But I do highly recommend you really try to understand dot products as multiplying components that are parallel, especially because we're going to get onto cross products next, which is multiplying parts together that are perpendicular. So, and they're useful in different situations. So this one is very useful in the idea of work, which you may have heard of in a physics class that you took. And the idea here is technically work, all right, is a scalar, is equal to the sum. So if you remember this from Calc 2, our integral, our sum of the force dotted with an infinitesimal direction. I'm going to put an L here, a dl. And so it's the sum of all of our little forces. So if we have some force being applied along some path like this, and we're applying a force in this direction and we're moving in that direction, this is F, some force F, and then we have our dl as we move in that direction, and dl, our teeny little itsy bitsy little steps along our direction. We have that. Now we can greatly simplify this to making it all be in just one direction, and therefore we can get rid of the integral if we keep a constant force in a constant direction, and we can actually change this to being the magnitude, or just change this to being F dot D, where F is the force and D is the direction and the displacement that is applied along, which we can then go back and do F, magnitude of F, times the magnitude of D, right? The magnitude of those times the cosine of the angle between them. And if we do that, we're good. And that's what we see in this picture here. We're moving at some displacement D, right there, right? Moving at some displacement D with some force F with an angle of theta between those two vectors, okay? And we can calculate the force. Because any part of the force here that's lifting up on it, that's pulling vertically, F in the y direction, let's say here, the vertical part, this vertical projection force is actually not helping to move it horizontally. So imagine if you reach down and you pull straight up on a box. If you pull straight up on a box, how much can you move it horizontally? And the answer is you're not going to move it horizontally. You can maybe lift it up vertically, but no amount of vertical force is going to move it horizontal. And the same thing here. So this vertical force here has absolutely no contribution to the actual work done moving it horizontally. And so the only thing we're ultimately interested in doing here is multiplying this projection right here, right? This projection right here, which is f in the x direction, which if we use our sines and cosines, that projection has this length, f cosine theta. And so what we're doing is multiplying this f cosine theta times the magnitude of this here. Those two are the parallel parts of each vector, the parts of the vectors that are parallel to each other, and therefore that is our work. And that's what we have right here when we do the dot product. The dot product is multiplying together the parallel parts, okay? And so that's what we get right there, and that's how we solve for it. So let's take a look here. I just wrote this on the previous page, but here's the work done moving something in a straight line with a force applied at an angle, a constant force. And so here you go. Let's try one of these. A box pulled 12 meters across a frictionless floor with a constant force of 10 newtons at an angle of 30 degrees above the horizontal. How much work is done moving this box, or how much work technically is done by this force on the box during this motion? And so we would say our scalar work is F dotted with D, which means multiply the parts that are parallel together. And so you can either think of this as F D cosine of the angle, like that, or you can think through of dot products and say, all right, I need this component of the vector, which is F cosine theta, times this distance here, this displacement that we're moving. So either way you think about it gets you the same result. Remember this vertical component here, this F in the y direction, it's not going to contribute at all, and so the dot product gets rid of it, and so does just our thinking our way through it of finding the parallel components gets rid of it. And we can just do, well, the magnitude of F is 10 newtons, the magnitude of D is 12 meters, and then we're doing the cosine of 30 degrees. And so we just multiply those all together, real simple. This is 120, all right, I'll come down here, 120 Newton meters, keep those units together, and then, and it's a scalar Newton meter, times the cosine of 30, and the cosine of 30 is square root of 3 over 2. And so this would be 60 root 3 Newton meters. There you go. And that's the work done. And a Newton meter is also known as a joule, if you want 60 root 3 joules, okay? But there you go. All right, and that is pretty much it for this section. Feel free to ask me or look into this some more, but again, I think it's a very good idea to start understanding dot products as multiplications of parallel components, okay? So you can eliminate perpendicular components, all right? So try some problems, try some thinking your way through it, try and get it to make sense to yourself, and really try to understand it before we move forward so that it becomes an intuition solving these problems rather than a memorization. It'll help you a lot going forward in math, especially when these ideas, if you ever move into something like tensors and things like that, where you expand these ideas into greater dimensions and stuff like that. It's really helpful to have a strong intuition and understanding about these things. All right, let me know if you have any questions, and I'll see you next time.